Now for finding R and S configuration theoretically, we are having a rule finding R and S configuration. This rule is also known as selection rule, and we are having postulates of this rule. The first postulate of this rule, priorities are given on the basis of atomic number and strictly not on the basis of electronegativity. Second, last priority group must be away from observer. If rotation is if rotation is clockwise, it is R. If rotation is anti-clockwise, it is yes. We'll take very simple example. First of all, I'll take example of fluorine, chlorine, bromine and iodine. All of you know that priorities are given on the basis of atomic number. So iodine is the first priority, bromine is second priority, chlorine is third priority and fluorine is fourth priority. First, give priority only 3 groups. 3. It is going in which direction? Clockwise direction. The configuration is R. But I have told you in Fisher projection formula, the group which is present in the horizontal plane, they are facing towards you. It indicates this fluorine is not going away from you. It is facing towards you. So in this case, you have to reverse the configuration. So configuration is yes. You can have another example also. So OH, NH2, Cl and CH3. The rule says priorities are given on the basis of atomic number. So direct connection you see. First of all, the chlorine. Second priority goes to the nitrogen and oxygen, OH, then NH2 and last is CH3. So first give priority only 3 groups, second, third, it is going in clockwise direction, it is R, but as this CH3 is facing towards you, this configuration is yes. Then now we will have more practice of this thing. Now we can take the compound containing 2 asymmetric carbon atom. We will take one more example each and we will proceed further. Please see, I will take a very simple example, CH3, OHH, OHH and CH3. Just now we have done, it is which type? AA type. Yes or no? How many optical isomer? 3. And this is erythro and this is meso. Means if we will get this carbon as R, we should get this carbon as S. Priorities are given on the basis of atomic number. OH will have first priority. Now say this is carbon, but this carbon is attached to OH, C3 and H. That's why we have to give priority carbon number 2. And then it is 3. So it is going in which direction? It is going in clockwise direction. So at carbon number 2, this is carbon number 2, at carbon number 2, it is going in clockwise, but lowest priority group is facing towards you. So it is yes. So 2 yes. At carbon number 2, it is yes. Now OH will have first priority, then this carbon will have second priority and this carbon will have third priority. It is going in which direction? Anti-clockwise direction. It is yes, but last priority group is facing towards you. That's why it is 3R. Please see, is it meso? So you can solve many more examples of this kind. Is it okay? क्या ज़्यादा लेना example?
चलेगा बस ठीक
है ना, क्या RS बच्चों को आता ही है. Now this is the R and S configuration. Now the most important thing, we have started with optical isomer. Optical isomer we have completed. Optical isomer, and now we are configurational isomer. Configurational we have divided into two types, optical isomer and geometrical isomer. Now what is meant by geometrical isomer? Very interesting concept. Now as we know that there is a sigma bond, so there is a free rotation. But when there is a formation of a pi bond, you know that there is a presence of unhybrid p orbital which will overlap sidewise, and there is a formation of a pi bond. So what is the difficulty in pi bond which is not present in the single bond? Single bond we can have a free rotation, but double bond, if we will do free rotation, one p orbital will be like this and another p orbital will be like this, the pi bond character will go and there will be no formation of pi bond. So here we are not having full rotation, we are having restricted rotation. What do you mean by restricted rotation? Till some moment we can have a rotation. Now the phenomenon of isomerism, due to the phenomenon of isomerism due to restricted rotation around carbon-carbon double bond. Very important. Free rotation around carbon-carbon single bond, it is known as which isomerism? Which conformational. And restricted rotation around carbon-carbon double bond, geometrical isomerism. Now geometrical isomerism, it is also known as cis-trans isomerism. Very interesting. You know that which compound will show geometrical isomerism? Very interesting. Please see, this is CH3, this is CH3, this is CH3 and this is H. Will this compound show geometrical isomerism? Will it show cis-trans? How? If I will write down like this, CH3 will remain as it is, and if I will change this, H and CH3, it is one and the same, so it will not show phenomenon of geometrical isomerism. What is the condition for geometrical isomerism? On both sp2 carbon atom, A must be not equals to B. Means if you are writing like this, hit A, this is B, this is A and this is B. So on both sp2 carbon atom, A should not be equals to B. This is the most important condition. Keep this thing in mind. This is the most important condition for the compound shows geometrical isomerism. Now please see, tell me this compound shows geometrical isomerism, yes or no? Yes. It is A, it is B. On this carbon, A is not equals to B. A and B is not equals to B. Done. This shows geometrical isomerism. Now please see, on both the CH3s are up, it is known as cis, and if it is known as trans. So they are geometrical isomers of each other. The phenomenon of isomerism due to restricted rotation around carbon-carbon double bond, it is known as geometrical isomerism. Now we are having a very simple phenomenon, that configuration is known as E and Z. E is intergene and Z is zooxanthous. Intergene means opposite, zooxanthous means together. Now how to, here also we are going to have a same thing. that priorities are given on the basis of atomic number. Please see, out of this sp2, this is 1, this is 2, there it is 1 and it is 2, 1 1 coming together, that's why it is having Z configuration. Done. Now if you are having two groups different, Br, I, Cl and fluorine, this compound shows geometrical isomerism. Yes, A is not equals to B. Please see, out of chlorine and iodine, number 1, number 2. Out of chlorine and fluorine, number 1, number 2. Groups are coming on the same side, that's why it is Z. I will write down another way. NH2, here it is OH, here it is CH3 and here it is Br. You have to consider sp2 carbon atom. This sp2 carbon atom, priority 1, priority 2, atomic number. This sp2 carbon atom, priority 1, priority 2. Please see, groups are opposite, that's why it is E configuration. So this is known as E and Z. I will have a very simple example. What is the configuration? Please see here, as this is CH3, this is CH2, it is attached to group, that's why it is having first, this is having second. And here there is a presence of hydrogen, here is a carbon 1 and 2. 1 1 together, that's why it is a Z configuration. Okay, so this is the E and Z configuration. Which isomerism is this? Geometrical isomerism. Now we'll have a fast discussion on whatever we have done up till now. We are going to have a very fast discussion what we have done up till now. Number 1, isomer divided into two types, structural and stereo. Structural into 5 type, chain, functional group, position, metamer and tautomer. Stereoisomers further divided into two types, conformational and configurational. Conformational divided into two types, free and restricted. Configurational further divided into two types, optical and geometrical. We have done each and everything, there should not be confusion. Now the most important part, when there is a restricted rotation, when there is a restricted rotation around carbon-carbon single bond. When there is an open chain compound, there is a free rotation. So when there is a restricted rotation, the restricted rotation present when there is a cyclic compound. And now our discussion will start with cyclic or cyclo alkanes. We are going to discuss about cyclo alkanes. Cyclo alkanes, this is cyclopropane, cyclobutane, cyclopentane, cyclohexane. two carbons cannot form the ring. That's why there is a no cyclohexane. Now, CH2s are known as methylene units. The CH2s are known as methylene unit. Now, when you are having this cyclopropane, the internal angle is 60. Here internal angle is 90. Here internal angle is 108. And for cyclohexane, internal angle is 120. Theoretically. This cycloalkane and our normal alkane, there is a great difference with the stability. The work on the stability of cycloalkane has done by the scientist Baer. And the Baer has postulated its theory, and that is known as Baer-Strain theory. What were the postulates of Baer-Strain theory? All cycloalkanes are planar. This was the first postulate. And second, stability of cycloalkane is given by normal tetrahedral angle minus internal angle. Means this is sp3 hybrid carbon. Now please see, this bond is 109 degree 28 minute. Now if you want to prepare cyclopropane, so this bond you have to bring like this, so it will become 60. So deviation from normal tetrahedral angle. So for cyclopropane it was 109.5 minus 60. For cyclobutane it was like this. For cyclopentane it was this much. It is found that cyclopropane, it is having highest angle strain, and cyclopropane was found to be highest unstable. It is true. Cyclopropane as a molecule is smaller, that it will remain in the plane and it is having highest angle strain. But as we go down and as we reach up to cyclopentane, it was found to be there was only 1.5. And according to Baer, cyclopentane was found to be more stable. It was planar. It is good. It's correct. It is planar. But what is going to happen as ring size is increasing? The molecule is not remaining planar. The carbon tries to maintain their bond angle 109 degree 28 minute by going in different directions. And they are adopting the different shapes. Here the Baer-Strain theory failed. What was the Baer-Strain theory? That 109 degree 9.5 minus 120, this difference was increased. It is increased. And when it is increased, it is found that cyclohexane and onward instability increases. It was not true. It was not correct. And cyclohexane onwards, because of the ring size increases, the molecule is maintaining its internal angle by 109 degree 28 minute and it is becoming stable. Here Baer-Strain theory failed. According to Baer-Strain theory, cyclopropane was highly unstable and cyclopentane was highly stable. Then Prelog and its co-worker has done lots of experiment. They have done heat of combustion experiment and they have found that cyclohexane, the molecule is maintaining its dihedral angle 109 degree 28 minute by adopting different size, and it is free from angle strain. It is free from angle strain. And here cyclohexane was found to be more stable. So cyclohexane it is more stable and it is existing in the different conformation. Now we are going to start with cyclohexane. Now cyclohexane, while drawing, please see, cyclohexane, red or green दोनों दे. Cyclohexane, this is having 6 methylene units. Cyclohexane exists in the two different conformation. This is known as the chair conformation. This is known as boat conformation. This is carbon number 1, 2, 3, 4, 5 and 6. This is carbon number 1, 2, 3, 4, 5 and 6. As I have told you, there is a restricted rotation. If we will rotate carbon number 1 and 2 and 1 and 6 restrictedly, we are getting boat conformation. And if we will do this restricted rotation, it will get converted into chair conformation. Now, in the cyclohexane, there is a presence of 12 hydrogens. Now, how these hydrogens are arranged, that we are going to see. This is 3, this is 4, this is 5, this is 6. 2, 3, 4, 5 and 6. First of all, we will draw all axial. What is meant by axial? Which is perpendicular to plane. So, first is axial down, second is axial up, third is axial down, fourth is axial up, fifth is axial down, sixth is axial up. Up it is known as beta and down it is known as alpha. So 3 beta and 3 alpha. Now each carbon contains equatorial. Here we have completed at carbon number 1 axial down. So first will be equatorial up. Second will be equatorial down. Third will be equatorial up. Fourth will be equatorial down. Fifth will be equatorial down. Sixth will be equatorial down. 3 alpha and 3 beta. This is the structure of chair conformation. Now, in the chair, we are having axial, we are having equatorial. Now, we are going to see how many different types of hydrogen present in the boat. Now, please see in the boat conformation, these hydrogens are known as flagpole hydrogens. And these hydrogens are known as bowsprit. These are equatorial and these are axial hydrogens. Now, chair conformation is more stable than boat conformation. Why? In the chair conformation, in the boat conformation, there is a flagpole hydrogen which will repel each other. That's why potential energy of the system will increase. And because of that, this conformation is more stable than boat conformation. Now we are going to have a look on different types of hydrogen in the chair conformation. Please see, this is the chair conformation. Carbon number 2, carbon number 3, carbon number 5, carbon number 6. It is in the plane. Carbon number 1 below the plane and carbon number 4 above the plane. First is axial down, second is axial up, third is axial down, fourth is axial up, fifth is axial down, sixth is axial up. Done. 3 beta, 3 alpha. Now equatorial, carbon number 1, first is equatorial up, second is equatorial down, third is equatorial up, fourth is equatorial down, fifth is equatorial up, and sixth is equatorial down. 3 beta, 3 alpha. This is the structure of cyclohexane. Now please see carbon number 1 and 2 and carbon number 1, 6 and 1. There is a restricted rotation. Now this chair, now it is converted into boat. When it is converted into boat, there is a flagpole interaction. So these hydrogens are repelling each other, making this system unstable. Now if we will see the Newman projection like this, please see all interactions are eclipsing interaction, and when eclipsing interaction is there, there is a which strain we have discussed previously, there is a torsional strain. So that's why this is unstable. And if you will have a chair, please see, and if you will see the Newman projection of this, there is a all staggered, and if staggered conformation is there, there is a no torsional strain. So chair conformation is free from angle strain because dihedral angle is 109 degree, and according to Baer, dihedral angle internal angle minus tetrahedral angle, so it is 0, free from angle, free from torsional. But boat conformation, it contains which strain? Torsional strain, because there is a which interaction? Eclipsing interaction. Now this chair conformation at room temperature, this chair is not remaining like this, it is converting from this one form to another form, and this phenomenon is known as ring flipping phenomenon. Now we are going to discuss the ring flipping phenomenon.